Okay, so problem 22. Now we've got to determine the pH, and we start with this concentration. Again, this is a salt made up of NH4 plus with the NO3 minus. Now that's the salt of a strong acid, nitric acid, and then this is going to be actually the conjugate acid of a weak base, right? NH3 is the base, and when in the presence of water, that's in equilibrium to make H2O. To make NH4 plus, and because it accepts a proton, that leaves behind OH minus. So this then becomes the conjugate acid. This is an acid, so in our equilibrium, it's going to be NH4 plus, that's the acid, in water, in equilibrium with, since it's donating a proton, it's an acid, H3O plus. I don't need to put that concentration brackets, I'm sorry. It's getting late and I'm sleepy. And that's going to then make that NH3 over on this side. What we know is the starting concentration here. It's 0.62. And then we're going to do an equilibrium calculation, but we need to know the Ka for that. And we're only given the Kb for its base. This is the conjugate acid. So again, we're going to have to use the relationship Ka times Kb is equal to 1 times 10 to the minus 14. So in this case, it's Ka is equal to 1 times 10 to the minus 14 divided by that Kb, 1.76 times 10 to the minus 5th. And that gives us our Ka for this reaction. And then I'll write. So I jumped ahead and I wrote out our ice table, then wrote the equilibrium expression. This is the Ka that comes from up here. So now just doing the arithmetic, this is a very small equilibrium constant, so that's small. And this becomes 0.62 times 5.68 times 10 to the minus 10 equals x squared, square root of both sides, is equal to x, which in this case is equal to our H3O plus concentration. And we want to know the pH. So that value here turns out to be equal to 1.88. 1.88 times 10 to the minus 5th. And so we take the minus log of that. So the pH, pH equal minus log of that 1.88 times 10 to the minus 5th. And that's our answer for number 22.